Bonjour et bienvenue à la chaîne. Hi and welcome to the channel. Today we are going to try and maximize the area of an n-sided cyclic polynomial. So what's the picture? So we have a circle like this and all the points of the polygon touch the circle. Touch them only once. And we have n sides, right? And we're going to try and maximize the area. So how can we make up the area of this? I mean, one way to do this would be to divide the polygon into n triangles, right? And then do this here. And then we see that each of these angles, I'm going to label as, I'm going to label this theta 1, theta 2, theta 3, and this one is going to be theta n. Now these are going to be our variables of our problem. And, without loss of any generality, just because it makes the maths easy and prettier, I'm going to assume that the radius of this circle is 1, but you can work with r, it's all the same. And now, how do we calculate the area of an individual triangle? Well, it's going to be half AB sine C, and A and B are 1 here, so this is going to be the area of an individual triangle is going to be half times 1 times 1 times sine of the angle. Let's just say theta I, right? For I equals 1 to n. And then you see that the area of the entire polygon is just going to be the sum of those individual triangles, right? So let's say area of poly equals the sum from n, I equals 1, of a half sine theta I. So I want to maximize this, but I need another constraint. So what's the other constraint? Well, these variables are not free, they relate to one another. They have to sum to 2 pi. So that's our constraint. So we have constraint is going to be the sum from n, I equals 1, theta I, well that's got to equal 2 pi, right? Of course. And also I guess these individual angles have to be less than pi and greater than 0. Right? Well, now we can use Lagrange multipliers. We have a constraint and we have a function, right? So let's construct a new function. Let's call it phi. And, well, what do you do here? You minus the 2 pi to get 0 on one side, and you minus lambda lots of this from our original function. So we have, now this is just the method of Lagrange multipliers. So, if you don't remember this, go look it up. So we want to maximize this function now. So minus lambda times, well it's going to be the sum from ni equals 1 theta I minus, well I have to minus the 2 pi from this side, so it's going to be minus lambda times 2 pi. Alright? I'm going to try and maximize this. Well, in order to have a stationary point, I need that phi differentiated with respect to theta, or theta I, for every single I, that's got to equal 0, right? At a stationary point, all the partial derivatives equal 0. So what's the partial derivative of theta, of phi, with respect to theta I? Well, let's just do that, right? So here, we have a sum. Sums are great to work with when we're differentiating, right? Because we only need to consider each respective part of the sum. Well, the only thing that contains theta I here, let's call it j. J will be better, right? The only thing that contains theta j will be when this I hits j. And then we're going to have the differential of a half sine theta j. Well, that's going to be half cosine theta j. Now, if we differentiate this part with respect to theta j, again, there's only one thing that contains theta j. It's going to be minus lambda, well, it's theta j differentiated with respect to theta j is 1, so it's just going to be minus lambda. And this has to equal 0 for all theta j. And of course, this is just a constant, So this, when we differentiate, it becomes 0 each time it vanishes. So this is our goal, is to find theta j such that this equals 0. And then we have a stationary point. Well, let's just rearrange. We get cosine theta j equals 2 lambda. Well, this is promising. This is promising. But what do we know about theta j? Well, we said it's between pi and 0, right? Well, let's consider the graph of cosine between 0 and pi. So it looks something like this, right? And we see, so let's say 2 lambdas here. We see that there's only one point, right? It doesn't repeat. There's only one point that would satisfy cosine of theta j is equal to 2 pi. It's 2 lambda, sorry. There's only one theta j that would satisfy that, right? So, this uniquely defines theta j, right? And this, remember, is for all j, ranging from 1 to n, right? So we see that theta j is in fact equal to theta I for all I and j. Now we don't really need to worry too much at this point of what this answer is. We just need to know that this uniquely defines theta j. So, we have a regular polygon. All the angles are the same. And if all the angles are the same, that's a regular polygon. That's the definition, right? Well, now let's go back to here. We have a constraint. Well, I want to consider what the actual angle is. We have the sum from n, I equals 1, theta I, and that's equal to 2 pi. Well, let's just call this, let's say it's equal to theta, without any subscript, right? So then, each angle is the same. Theta I is equal to theta j for all I and j. Well, now we see that this theta doesn't depend on I, right? So this is equal to, well, I'm just adding theta n times, is equal to n times theta. That's equal to 2 pi divided by n. And I'm going to get 2 pi divided by n. Exactly as we'd expect. Boom. There we are, regular polygon. Now if you're interested, I'm going to derive the actual expression for the area of the polygon. So we see here we have the sum from n I equals 1 of a half sine theta I. Well, we said theta was 2 pi over n, so it's sine 2 pi over n. And again, this no longer depends on I, which is the perfect thing, which means we're just adding a half sine 2 pi divided by n times. Which means we just get n over 2 sine 2 pi over n. Perfect. So now what happens is our number of sides goes to infinity, let's say. Well, I'm going to say that this is equal, I'm going to say, let y equal n over 2. And you'll see why I'm doing this in a minute. So we consider the limit as n goes to infinity. Well, as n goes to infinity, y goes, apologies for this, I meant to say 2 over n. And as n goes to infinity, y goes to 0. So as the limit as n goes to infinity, if that was what I was considering earlier, well, now let's consider the limit as y goes to 0, right? So let's consider the limit as n goes to infinity of this. Well, that's the same thing as the limit as y goes to 0. We see it's n over 2, and that's the reciprocal of what I've got. So that's 1 over y times sine, well it's 2n, which is y, times pi. So it's pi times y. Well, now let's times top and bottom by pi, right? I can do that, I'm not changing anything, so times, so I'll do this meter. So times the top and the bottom by pi, right? Well, I know this limit. This is a very famous limit, right? The limit as the thing inside the sine divided by the thing goes to 0, that's 1. And the pi is independent of y, so I can take it out. So this is in fact equal to pi times 1, which is pi, which just so happens to be the area of the actual circle. It's pi r squared, r was 1 here, so the area of the entire circle is pi, which is equal to the limit of the area of the polygon as n goes to infinity. Wow!